When I said 41, I started going through the slides, and it was the same problem, just verified over and over. The next unique slide, and again, I just showed all my work on the same slide, and they're showing it step by step, is why it's taken so many pages. But I'm finding page 47 that offers me a next example. It asks us to compare the effect on pH of adding 0.01 moles of a strong base like sodium hydroxide to a buffered solution of a weak acid and its conjugate base, to just adding straightforward sodium hydroxide to pure water. So here's what we're saying. This is the same calculation we went through a moment ago. We found the pH of a buffered solution. We added a strong base. It initially started at 4.745 or 4.75. It went up a little, but not much. Compare that to just straightforward sodium hydroxide in pure water. We get a pOH of 2, turning that into a pH of 12. A buffered solution significantly holds the pH in place. Without the buffer, we'd expect it to be 12, and yet it just nudged a little bit from 4.5 to 4.83. So this slide is just emphasizing the purpose of a buffer. It's a system of chemicals added to a solution to help resist a change in pH. Really absorbs like a sponge. It absorbs excess base or excess acid to help maintain the pH within a specific pH range. Very important for homeostasis in our body, for example. pH of our blood, 7.4. We can't stand strong swings of pH. If I eat a tomato that's completely acidic, I don't want my blood to swing toward the acid range. We have systems of buffers in our body to help that from happening. Well, let's take a peek at a new example. Calculating the pH of a buffer that has 0.14 moles of an acid, 0.071 moles of its conjugate base, and this time I'm going to add a strong acid to it, and it's okay to assume that X is small. Let's get a handle on our equilibrium. Equilibrium comes from the dissociation of the weak acid, HF. What we know, the initial moles, 0.14 for the acid, 0.071 for the base, or the conjugate base, fluoride, coming from the common ion in potassium fluoride. 0.071 moles of the conjugate base. We know 0.14 moles of the conjugate acid. They tell us pKa, awfully nice, 3.15. So here's initially the equilibrium. To this equilibrium, we add 0.02 moles of the acid HCl. We're adding acid to this system, 0.02 moles worth. So adding acid to the system is going to use the base and make more acid. Let's get that diagram back out, that bar chart that I have close by. Initially, we have an acid and its conjugate base, same amounts. If I add acid, we make more acid and use up the base. Previous example had a swing to the right. Here we're adding acid, so we make more acid, use up the base. More acid is made. So I'm going to add 0.02 moles, and I'm going to subtract 0.02 moles. Think about it in terms of Le Chatelier, if that helps. If this is the stress, adding more acid, the stress adding more says point away from it. To point away, we make more molecular acid, and we consume the F negative. Adding more H positive shifts this equilibrium left according to Le Chatelier. So at the end of the reaction, the number of moles, 0.14 plus O2 is 0.16 moles. I double dotted my decimal, sorry. The fluoride now got consumed, so I was just doing math in my head. 11 minus 2 is 9, so that's 69.069 moles. No, that's not right, Linda. 0.071 minus 0.02 is 0.051 moles. which makes me check here. 0.14 plus 0.02 is indeed 0.16. We want to know the base and the acid after the stoichiometry has been done. We're now ready for Henderson-Hasselbalch. Step 1, stoichiometry. Step 2, Henderson-Hasselbalch. pH can be found by taking the negative log of the Ka. That's called pKa. Oh, I don't need that. My bad. Pretend I didn't write that. We want it to be pKa. We don't need a negative log. It's already there. pKa. I'm going to write this down. I apologize. I'm making it better. pH is pKa plus the log of the ratio of base over acid. Henderson-Hasselbalch. Since they gave me pKa, that's what I need, just directly into the formula. pKa is 3.15. Then I take the log of the ratio of base, 0.051, over acid, 0.16. And those are big M molar units. The volume of our container was 1 liter, so moles per liter will match. And we'll hit it. 3.15 plus the log of the ratio, 0.051, over 0.16. And we get a pH of 2.65 units. Stoichiometry first, adding acid made more acid, consumed the base. Take the new values into the Henderson-Hasselbalch and solve for pH. Let's see ahead how many slides it took to get us there. Is that the same problem? 0.071, 0.071. Aha! Slide 53, 2.65 pH units. Perfect work.